mention another method that's related called ensemble selection. First, a few announcements. So the Kaggle competition, which is mini project 1, will be released in a few days. It will be a team-based project, so you work in groups of 2 to 3. We release a data set, you download the training set, you train the classifiers, and then you upload your predictions, and then we have a leaderboard. And at the end of the competition, we'll see who wins the competition. There will be a public leaderboard and a private leaderboard, so what that means is that you can actually overfit to the public leaderboard if you're not careful. And that has happened in the past, where someone got first place in the public leaderboard because they're tuning their parameters and inching their way up the public leaderboard, and they were not first place in the private leaderboard, which is the one that counts. At the conclusion of the competition, you'll submit a report of what you've done. Very standard template, should be fairly straightforward. Any questions on that? Yes?
Are there going to be homeworks at the same time?
Yeah, so the deep learning homework comes out on Friday. And so this will have about 1.5 week to 1 week overlap with the deep learning homework. And then after the deep learning homework is due the week later, you have nothing except the Kaggle competition. So most people will spend the majority of the time, basically 1 week, working on the Kaggle competition. Many students express an interest in just taking a look at it, having had thought about what they're going to do. But I expect the majority of you will spend most of your time working on it in the last week, basically. Okay. Today I'm going to go over a high-level overview of ensemble methods, most notably boosting, which is an ensemble method for reducing bias. So last time we looked at an ensemble method for reducing variance called bagging. And then I'll close with a discussion on ensemble selection, which is another method. So just to recap, there is some unknown true distribution of data, of XY pairs where X is the input and Y is the target label, that is unknown to us. We assume that we have access to a finite training set. Each example is sampled from this true distribution. So each example being an XY pair right here. Right? And the goal then is to train a predictor or a hypothesis, H, I'll use H here, which is a function of S, which is a training set, that minimizes this test error that we can't directly measure. Right? And overfitting is the case when the test error is much, much larger than the training error. That's conceptually what overfitting is about. Right? And so, the training set, just as a simple pictorial example, is sampled from this test distribution which we don't directly observe, right? And if we train a model that achieves this level of accuracy on the training set, we want to be able to sort of measure what it means on the test set, or at least have some sort of way of reasoning about what it might mean on the test set, right? And so this is just review. So we can treat, the predictor as a random variable if we think about it as a function of the training set, right? If the training set itself is a random variable in that we assume that it is sampled from the test distribution, which meant if we were to somehow repeat this process and collect a new training set, we would get a slightly different classifier or regressor because the output of this optimization problem is a function of the training set, which is random. Right? So then you can talk about the expected test error of the model class by taking the expected test, by measuring the test error of some particular model in your model class, trained on this training set, over the randomness of the training set collection process. Right? Again, just recap. Bias variance decomposition is one way to think about the expected test error of a model class. For square error, this has a very nice mathematical form that decomposes very cleanly into a variance term and a bias term, where the bias term is simply the deviation from the true label of some test example versus the average prediction of over your model class, of the randomness of the possible training sets you could And the variance term is the deviation of any particular model you would train from the mean prediction. Right? So it has this nice clean decomposition. And so in bagging, we looked at a way to reduce the variance term. And today we'll be looking at a way of reducing the bias term. So this is just a recap of the bias variance composition for one-dimensional regression, where we looked at linear, quadratic, and cubic model classes. And here we get this very clean separation, at least when we measure it as a square, of the bias, which is the deviation from this average prediction to each of the test examples, and the variance, which is the deviation which is the average deviation, square deviation, is the variance, of any particular model in your model class relative to the average prediction. And so, some models experience high test error due to having high bias, which means that the black line, right, is very wrong. And so this model class is perhaps misspelled too. Don't mind that. Too simple to make accurate predictions. Other model classes, you experience high test error due to high variance, right? Because even though on average the model class might be able to make good predictions, any particular model that we train, at least for this size training set, could make really bad predictions, right? And so that's the case here for the cubic model class in the case of 7 training sets of size 7, right? So the model class, in other words, the model class is unstable due to insufficient training data. Okay. So as a general concept, an ensemble method is basically a machine learning approach that is a collection of models that were trained using some baseline machine learning approach, and then combines the predictions of these different predictors or models into making a single prediction. So in the previous lecture, we looked at bagging and random forests, right? And today we'll look at boosting and then close with ensemble selection. Right? You can think of this as sort of like a meta-learning approach, right? It does not innovate on the base learning algorithm or model, right? It doesn't innovate, or with the exception of random forests a little bit, it doesn't really innovate on like decision trees or SVMs or things along those lines, right? It's not concerned with how you actually train each individual model, right? An example with bagging is, create a new training set using the bootstrapping method from statistics, and then you call some machine learning algorithm. You don't care what it is. In the previous lecture, it was a decision tree learning algorithm, right? And then you average the predictions of the various training models. That's what I mean when I say this is a sort of like a meta-learning approach. Any questions on this? Okay. Okay, so, one way to think about why ensemble methods might work, like might be a reasonable thing to do, is to view it through the lens of the bias variance trade-off, right? So bagging reduces the variance of low bias models. So you have a very expressive model class that suffers from high variance but has very low bias, such as minimally regularized decision trees, right? Then, these low bias models are very complex and are unstable because we don't have enough training data to train them in a stable way. What bagging does through generating bootstrap samples, therefore simulating collecting multiple training sets, right, is we simply, train a bunch of these low bias, high variance models using bagging, and then we just average them together to create more stability, right? Today we'll be talking primarily about boosting, which reduces the bias of low variance models. So if you have a very simple model class that forms your base components, right? They have high bias and low variance. They're very stable, but they don't have much expressive power. How do we combine them to form a more complex predictor so that the sum of simple models is more complex and accurate? Okay, so that's what boosting will do. Okay, so boosting, also known as the strength of weak learners. So first, a little bit of terminology. So we're going to call a shallow decision tree as a decision tree with only a few nodes. So a heavily regularized decision tree. Shallow decision trees have very high bias and very low variance, right? Different training sets typically lead to pretty similar trees. The error, though, is pretty high because a decision tree with only one node of decisions is simply just the axis-aligned linear classifier, right? Which is the extreme case known as a decision stump. A decision stump is the extreme case of a decision tree with exactly one split, right? in which case you just get a simple axis-aligned piecewise static function. Right? That's your function class. So, you know, shallow trees tend to learn more or less the same model. So our model class is a function of the randomness of the training set at a low variance, right? So now if we get this as our training set, right? We have a two-dimensional training set. This is our classifier. We resample from the training set. We get something like this. We resample the training set from the true distribution. We get something like this. We get classifiers like this, right? And so on and so forth. Okay. So a decision stump is known as a weak learner in the terminology that I'm going to use today. So you can think of an error rate, at least for classification, as the error rate on over some distribution. Typically, the true distribution. You could also this could also be the training distribution. And a weak classifier, this is sort of an informal definition, is one whose error is slightly better than random guessing. Right? And a weak learner is some learning algorithm that can learn a weak classifier. For example, top-down induction for decision stumps. Right? So shallow trees are weak classifiers, and weak learners have low variance and high bias. So how do we boost the performance of a weak model? Right? Right? So this is the expected test error. Again, I'm just writing down the error in terms of squared loss because it has a nice mathematical form. Weak models have high bias and low variance, right? Because they, if you sort of look at the output of this function over the randomness of the training sets, the variability relative to the average prediction is pretty low, right? But this term can be quite high. You're going to make a lot of mistakes, right? So bagging doesn't work, right? If your model class are decision stumps, bagging actually won't improve the performance much, right? If you bag a bunch of decision stumps. Right? And so let's think of that. So I'm going to introduce boosting here with a simple operational example, right? For regression, we'll talk about classification later on in this lecture. Let's start with regression because it's conceptually a bit simpler. And we're going to do one-dimensional regression, right? So we're going to have a single x, right? And then we have a target that's 1. And so this is, if you take a look, it's a quadratic function. We don't know that it's quadratic. We're just going to learn this using decision stumps, right? And so, interesting. Formatting is a little bit weird. I have a pet peeve with this projector. Okay, so this is not the way it looked. Okay, why this should be that big a deal. So we're going to learn the first decision stump that minimizes squared error on this training set. Apologies for the format. And so it's going to learn to make a decision between between the first 4 and the next 2, right? It's going to put the decision right here, and then the first 5. And for the first 5, it's going to predict the average y, right? So this is one child node, and then these 2 form another child node. And then for the bottom 2, it's going to predict the average, right? And so that is the best you can do with a single decision stump if you want to minimize squared error over the child nodes, right? And then what we're going to do now is we're going to create a new training label. So for every x, we're going to create a new training label, right? And this training label is going to be the residual, right? So in this case, this set of training labels in the second iteration of learning, or the second round of learning, is simply the difference between the prediction of the model that we trained, the first model that we trained, with the ground truth, right? So here the ground truth was 0, right? And the prediction is 6, so the residual is -6. Right? That's all we're going to do. And so we get a different residual for different input instances. Right? And now we're going to create a training set. We're going to create a training set where the x is again this x, but the y's are these y's, okay? And so we're going to train a second model, a second regressor, to make the best possible prediction on these y's given these x's. So that's your training set. These x's and these y's. And then you'll get a decision stump. We're going to train a decision stump that looks like this. So it's going to predict, it's going to decide to split these two and these 5, right? And I'll make the average prediction over the training data, the training labels in this child, and make the average prediction of the training labels in this child. Right, so now we have our second model, right? And then our overall model, right? Our overall model, the model that we're going to, our ensemble, if you will, is simply the sum of all the models that we trained so far, right? So that would be this, right? This would be the sum over all the models that we trained so far. And this process continues, right? So, we create the third set of training labels we create is the residual between the ground truth and the sum of the first two models, right? And so that's what the target labels look like. And so now we have a training set of these x's and these y's, right? And we create another, and then we train another decision stump on those, and then this is the average of the sum, of all three models. And so we could also look at what this looks like pictorially, right? So this is the x, and this is the target y, right? So there's a quadratic function. You learn this decision stump at iteration 1, right? That looks like this. So this is the left child, this is the right child, right? And then the aggregate predictor, the ensemble, since it's a singleton set, it's just whatever the first predictor was. The training signal, the training set for the next time step is on the y's are the residuals between the ground truth and the prediction of the aggregate predictor before. And so this is the training data. This is what the training data looks like. We train a model that minimizes square error on this training set. Again, it's a decision stump. So it makes only a single split in this one-dimensional feature space. And this is what the model looks like. And then our aggregate model is the sum of these two. Right? So it looks like this. Right? And now we do it again, right? So this is the residual between the ground truth and this prediction. Okay? And we train a model. It looks like this. And then we aggregate, and it looks like this. And we can keep doing this, right? So that's basically how this process works. And so what I just described to you is what's called gradient boosting, right? The simplest version of gradient boosting, but it's called gradient boosting. And so basically, a little bit more formally, right? You have a training set, right? And then you're in the first round of learning, your training set is equal to the original training set. You train a shallow decision tree. In this case, I'm just showing a level 2 level decision tree, but it could be a stump. And you have a predictor, right? And then the predictions of these guys, plus it is used to create a new training set where you only look at the residuals, right? Train a new predictor, and so on and so forth. So what we're doing is we're essentially creating a sequence of training sets, right? And we're learning a simple model on this sequence of training sets, right? And then we're combining these models together to create a new, hopefully more complex model class, right? Any questions on how this works, at least operationally? Yes?
How do we make the split? Like where
standard decision tree training. So this is a meta learning algorithm. We don't, like this arrow, like from the perspective of this approach, is a black box.
Okay.
Right? So, for regression, it would be minimize the squared error of the predictions of the two children. That's it.
Okay.
Yeah. So yeah, think of the learning algorithm as a black box. It's a function call that this meta algorithm calls. Okay. Right. Yeah. Yes.
Why is training another tree on residuals different from just making the first tree deeper?
Why is it different? Well, so if you look at the function class, right, it's certainly true that a super deep tree can express anything that is a sum of these. That's true. So in terms of the analysis, right, if you make the assumption that each of these trees, right, these shallow trees is stable, right, has low variance, right, then this combination will reduce the bias of the aggregate model class. Whereas you can't make that same claim by when you train a single tree. If you actually look at what the predictions are like, right, they're sort of overlaying sort of these linear, piecewise static linear splits of the space on top of each other. Whereas here, when you train this guy, right, imagine this is a complicated tree, like a simple tree, right? If you train this guy, this is only splitting this data, right? This is only splitting this data. Whereas this guy is splitting all the data, but with a different target.
Okay, so it's because you're mixing in different subsets.
Yeah, that's right, yeah. Does that make sense? Yeah. Okay, so to understand why this method is called gradient boosting, I want to sort of draw an analogy to axis-aligned gradient descent for a linear model class. Okay? So recall that a linear model, I'm omitting the bias, the offsets for simplicity. It looks like this, right? And we're going to minimize squared loss, and we're going to do gradient descent. We're going to do gradient descent on squared loss on this training set with a linear model class, where we're only going to allow axis-aligned updates, right? So we're only going to allow updates along a single basis, along a single axis of the model class, of the feature space, right? And so what that means mathematically in practice, typically, is that you compute the gradient, right, of your, and here I'm not doing stochastic gradient descent here, just gradient descent. You compute the gradient of your loss function, that's g, right? And then you simply project it to the dimension with the greatest projection, right? That's how you do axis-aligned gradient descent. This is also known as coordinate descent, right? Because you're doing gradient descent along one of the exactly one of the coordinates of your representation of your model class. Right, so here's just a very simple picture, right? So if we have two axes in our model class, right, and this is the gradient, we would project to one of the coordinates or axes, typically the one that has the larger projection. Yes.
What are you using to evaluate the size of the gradient? Any specific norm?
Typically, it's just cosine similar, so 2 norm. Okay. Yeah. Okay. So you can think of a linear model as a combination of one coefficient per feature, right? And so an ensemble method you can think of as one coefficient per model, right? So an ensemble method is somehow, if you've taken any kind of analysis course, you can think of it as a linear function over a function space, right? And so, imagine that this is the space of all possible shallow trees, right? The space of all possible shallow trees, right? And we're going to learn a linear model. Our goal is to learn a linear model over this function space, which is the span of all shallow trees. Now, the dimensionality of this space is potentially infinite, right? But that's okay. And so here, there's a coefficient of 1 in this particular case if this model is used, and 0 for if the model is not used, right? So most coefficients here are going to be 0. Right? If we had a finite number, of trees that we're learning over, then we're going to learn a linear combination over a finite number of trees, right? Just like a linear combination over a finite number of features, right? So these features are just axis aligned in terms of the raw coordinates, the raw input features. Here it's somehow we're going to be axiomatic over some simple model class. Right. So this is just sort of general properties of function spaces that people typically like to have for their function spaces. You know, for well-behaved function spaces, you can think of it as a generalization of a vector space, right? So it's closed under addition, it's closed under scalar multiplication, and gradient descent, you know, or at least axis-aligned gradient descent, is adding a scale function of one of your basis functions, in which case our basis functions are shallow trees, to the existing function class that we're learning, right? To the existing function that we're learning. Right, so every quote-unquote axis of this function space is a weak model. Again, there is potentially an infinite number of axes or dimensions in this function class. And all the models that we're learning, ensemble models, are thought of as linear combinations of weak models. So it's just learning these coefficients in some function space, right? Any questions on that? Yes?
Are you assuming a Hilbert space to make it so that you don't have to deal with like dual spaces when?
I am not assuming this is a Hilbert space, no. This is simply some function space. I mean, I think it suffices just to think of these as just an infinite. It suffices to think of this just as an infinite dimensional space of models that we're learning a linear model over. Yeah. Yeah. It doesn't need to be a Hilbert space. Right. So essentially what we're doing is if this is the loss that it minimizes, if this is the gradient that minimizes the loss, well, we can only learn in this case one of two shallow trees. This shallow tree somehow minimizes the loss more than this shallow tree, let's say. Or I guess the example is more clear with this guy. This shallow tree somehow minimizes the loss more than this shallow tree. If this is where your ensemble is right now, then we want to add this shallow tree with this magnitude, right? So, functional gradient descent basically says we want to compute the gradient of the loss and then project it onto one of our basis, on one of the dimensions of our function space, which is one of the dimensions of one of the weak models in our function class, right? So, in the case of a linear model where the h's are just dimensions of the raw feature space, this is a simple projection operator, like a cosine similarity type of projection operator. In the case where, and then you sort of do a for loop over all possible dimensions, and then you just pick the one with the highest projection. In the case where you have an infinite dimensional function space, right? Then we have to find the optimal projection by solving an optimization problem. In this case, learning the best possible shallow decision tree. That's sort of the main conceptual leap here is that when you're doing coordinate descent in a linear model where each of these h's is basically one of the basis vectors, right? Then you just write a for loop over all your dimensions and then compute and then use the dimension that has the largest projection of the gradient. When you have an infinite number of dimensions, such as when you over a function space of weak learners, spanned by weak learners, over a function space spanned by weak learners, then we have to solve an optimization problem because there's an infinite number. There's potentially an infinite number of such axes. Right? But if we can solve this optimization problem, then like at a high level, we're just solving this projection problem as well. Any questions on that? Right, so yes, I've talked enough about this, that this is just a recap, right? Weak model is an axial unit vector, same function form. So I guess I already alluded to this. And so here's the more full version of gradient boosting. The main difference is that you have these coefficients here, right? before, these coefficients were either 1 or 0, right? And now they can be something other than 1 or 0. I won't go into the details. If you're interested for how to set these coefficients, there's a really nice paper linked to here. Okay, so just a recap of basic boosting, right? It's an ensemble of many weak classifiers. The goal is to reduce the bias of these low variance models, which are weak classifiers or weak regressors, I should say. And the derivation is, or one way to view the derivation. There are actually multiple ways of deriving the same algorithm. I should mention that there are multiple ways of deriving the same algorithm. I presented to you a viewpoint from the perspective of gradient descent in function space. Right. Yes?
Is there a theorem on what kind of functions you can express using these linear combinations of decision stumps?
I'm not sure. Actually, I'm not sure. I'm not sure about what you can say about the expressivity.
Okay.
I don't know if it's equal to training a single expressivity of a single decision tree. I suspect that it's less expressive than a single deep decision tree. I suspect that it is, but I'm not sure. Okay, so what I presented to you was a boosting algorithm for regression, right? Now I'm going to talk about a boosting algorithm for classification. This is one of the most famous algorithms in the machine learning literature, AdaBoost, which stands for adaptive boosting. Okay, so gradient boosting, as I presented to you before, was designed for regression. Can we also design one for classification? And so AdaBoost is, again, it's also an instance of functional gradient descent, right? It has the following form. So the ensemble classifier takes the sign of a bunch of base classifiers weighted by some coefficient, right? So the base models are all classifiers, so binary classifiers as opposed to regressors. Right. And so here's how we can combine multiple classifiers. So we have this aggregate scoring function, and then we take the sign. Right. So imagine that we have these 4 data points, right, x1 to x4, and suppose we had these 4 models. We had these 4 weak classifiers that made these binary classifications for these 4 instances, and our F basically has these coefficients, and these are the scores. Then our ensemble classifier would basically predict the sign of these scores. And so the question then becomes, how do we learn this sequence of base classifiers, and how do we determine the coefficient? But otherwise, that's basically the form of the ensemble classifier that we're going to learn using AdaBoost. Any questions on this? Okay, so like in gradient boosting, we're going to also go through a process where we create new training sets, a sequence of new training sets, and each of these new training sets will form will be used to call some weak learner that returns to us a weak classifier, right? And how we do that is a black box. We don't care as long as there's some weak learning algorithm like top-down induction of decision trees of depth 2 using entropy, impurity, whatever, right? So now we're going to talk about how to create do this whole process for classification, right? And for classification, instead of changing the target label, which is what we did in regression, we're going to actually reweight the different data sets. Right? The different training examples in the data sets, right? So let's define capital D as a weighting over the training example. examples, right? And just to make things well conditioned, we'll assume that it sums to 1, right? And it's non-negative, right? So the canonical example is to weight every data point uniformly, right? So if we have a training set of size 3, we would weight each of them 1/3. This is equivalent to just weighting everything uniformly. We could also say, well, you know what? We don't actually, we're going to create a training set where we don't care about the first example, right? But we care about the second and third one equally. And then you could do other more complicated weightings as well. And then and our loss function is this weighted loss function, right? So when this weighting is uniform, this is basically equivalent to minimizing the original loss function, right? Scaled by just a constant factor. So when you're training decision trees using this weighted training data, it's almost the same as training normal decision trees, just a very, very slight modification of the split criteria where you weight the examples, right? So here is how the algorithm works. We start with the first weighting being uniform, so we're solving the original weighting problem, right? We're going to train a shallow decision tree, and then we're going to have this classifier, right? And then and I'll tell you later the formula, we're going to determine a weight for this classifier as a function of how well it performed in the training set, right? And now we're going to take a look at our ensemble. We create a new weighting of our training set. So some examples get weighted more, some examples get weighted less, and then we train a second classifier based on this weighting, right? And then that process continues. Man, this projector really is doing a number on the format. That is basically how AdaBoost works. And then the question then is, again, how do you choose the weighting? How do you choose these coefficients? Okay. So let's think about the intuition. Let's think about if this is our current model, right? This is our current model. This is the scoring. This is the raw scoring function. The ensemble classifier takes the sign of the raw scoring function. So this is the raw score of the current ensemble that we have so far, and this is the decision, right? So these two examples, right, are very far from the decision boundary, right? So this one is classified. This one is scored a very large positive number, and the label is positive. This example scored a very large negative number, and the label is negative. So if the next model we add to this thing mispredicts these two by a little bit, it's probably fine. The ensemble will probably still classify these two accurately, correctly, right? This guy is somewhat close to the decision boundary, right? Like, relative to these two guys, for this example, the scoring function is close to the boundary, although it still gets it correct, right? And this guy violates the decision boundary, right? We actually make a misprediction for this guy, right? And so, here's a thought experiment. Like, if we train the next, suppose we were figuring out a weighting of these examples, right? These examples. And we're going to train a new weak classifier to add to our ensemble score. What happens as a thought experiment if this weak classifier mispredicts on everything, right? All four of these examples, right? So here's just the same thing, right? And so for simplicity, let's just make the coefficient 0.5, just for the purposes of this thought experiment. Just make the coefficient 0.5. Right? So then in the worst case, if the H5 that we've trained mispredicts on all of these, right? Then this would be the new aggregate scoring function, right? And so let's think about the impact on this to the aggregate classifier, the ensemble classifier, right? So it would be kind of bad here, right? Because we're going to get closer to the decision boundary. Right? It's irrelevant here. We still have a really high number, right? We're still very far from the decision boundary. It's irrelevant in the fourth one example also because we're still pretty far from the decision boundary. And it's pretty bad for the third one because we move even further into the wrong direction, in the wrong side of the decision boundary, right? And so this intuition should give you some sense of, maybe we can create a training set where we give this guy a very low weight, right? Give this guy a very low weight, give this guy a pretty high weight, and give this guy a very high weight. And that should be the weighting, intuitively, that we should give to the next training set to train our base classifier up, right? Does that make sense? Any questions on that? Right, so what we want, so just to rephrase everything in a slightly different way, what we want is we want our next classifier to definitely classify this guy correctly, right? Should probably classify the first guy correctly, and we don't actually care. You can misclassify the second and the fourth examples, but it actually has a minimal effect on the overall ensemble. So the desired weighting should be low, low, medium, high. And we'll make this mathematically precise in the next slide. But that's the intuition. Okay, so here is the AdaBoost algorithm. We initialize in the first round of learning, we initialize the weighting to be uniform, right? And then we train the best possible decision stuff on this training set with this weighting, right? Using, again, the learning algorithm is a black box function call, right? We compute error on this training set, so this is the error, right? And then we define a step size. This is the alpha, that's the A or alpha, that's the coefficient that you put in front of every weak learner. And this is the formula. It's a function of the error we obtain. So if the error gets close to 50-50, then this thing just breaks down. So the error has to be slightly below 50%. Right? And then we do an update, right? So the next weight, right, is basically you take the weighting from the previous iteration, right, and then you multiply it by this factor. And I'll walk through what this means in a little bit. And then we normalize so that this guy sums to 1. Right? And at the end of this whole thing, we return the ensemble. So this is the entire AdaBoost algorithm. It's basically a Python for loop around your favorite machine learning algorithm. Right? Yes?
What's your loss function you're using?
I will get to that. It's called exponential loss. And I'll get to that. Well, it's actually literally this term right here. Right? So I'll get to like one of those curves that compares to 0-1 loss in a few slides. Okay, so just a simple operational example, right? We have our original training set. It's pretty big. We have our weighting. In this case, I guess we have 100 examples. We train our first model, right? It has some H1. It has this error, 0.4. So it's a weak learner. So it still gets pretty high error. It has a high bias, but it's a little bit better than random guessing. And then, using this formula, we set the coefficient so that this is our first model. We get this new weighting that is a function of weighting these guys by multiplied by this term. So if we get an example, let's see, if we get an example incorrect, right? So then this product y times the h sub t, this guy, is going to be negative, right? So then negative a to that will get to a large positive number, so we're going to weight it more, or a positive, a number bigger than 1, so then we're going to increase the weighting. If y times the score, times the classification is, they agree with each other, this will be positive, and e to the minus a times that will be negative, so then that's a number, negative a times that will be negative, sorry. So e to that will be less than 1, Therefore, we decrease its weight, right? And that's what you see here. This guy was classified correctly, and so we decrease its weight by a multiplicative factor equal to this. This guy was classified incorrectly, so we increase its weight, and so on and so forth. And then, of course, we sum up all the d's and divide by z so that the new d's sum to 1. And so now this forms the weighting for the next training set that we're going to train our weak learner on, right? And then we train a weak learner. Let's say it has an error rate of 0.45, and then according to this formula, we set the step size of the position to be 0.1, and then it got this one correct, this one correct, this one wrong, this one wrong, and then we can create a new weighting according to this guy, right? According to this formula. This guy was, again, classified correctly, so the weight goes down even more. This guy was classified correctly, so the weight goes down. This guy was classified incorrectly, the weight goes up, and so on and so forth. And this process continues. Right, so if we ever get an error rate of 0.5, that means the model is basically equivalent to random guessing. This whole process actually breaks down. So we assume that that doesn't happen. Any questions on this? Yes?
So if the model performs like really bad so that the error rate is like 0.5, the A becomes 0 and that model becomes like also E.
Yeah, but then you also become stuck, right? You don't have a way of creating any weights, right? So you become stuck. Yeah. You can't make further, according to the structure of this particular algorithm, you cannot make any more progress. So this whole approach assumes the existence of weak learners. A weak learner is something that can learn something a little bit better than 0.5. Right. Okay, so someone asked the question of what is the loss function that this process is implicitly optimizing over, and the loss function is known as exponential loss, right? And that is the definition of the loss function right here, right? So if your scoring function, so here it's typically a written expression of the scoring function. So if the true label was +1, right? If the true label was +1 and our score was a large positive number, then the exponential loss is going to be close to 0. In fact, it goes to 0 exponentially quickly. If the as the scoring function becomes smaller, it's more and more negative. If the target was 1. Then it's going to become this big number, and again, it upper bounds the 0-1 loss, right? And in fact, this looks a lot like the weighting scheme, right, in the AdaBoost reweighting process, and we will prove in the homework, and if somebody probably already take a look at the homework, that AdaBoost minimizes exponential loss iteratively. So if you look at if this is your loss function, right? Remember that recall that this is the aggregate scoring function, right? Before you take the sign, so it equals this, right? And so it equals the sum of the scores of the base classifiers, which if you just sort of move the sum outside of the exponent, you get a product, right? So you get something like this, right? And that is exactly the distribution update rule. Right? How much we upweight or downweight any particular example is equivalent to is proportional to its exponential loss. So as an example, as an example suffers higher and higher exponential loss, we're going to upweight it proportionally. Of course, in the actual distribution, we normalize so everything sums to 1. But this is basically what's going on. So exponential loss operates in the exponent space, right? So an additive update to F, our ensemble model, equals a multiplicative update to the exponential loss, right? So the reweighting scheme in AdaBoost can be viewed as something like the minimizing the residual exponential loss. So this is the AdaBoost algorithm, right? So the update rule is reweighted according to the exponential change in exponential loss. So AdaBoost iteratively finds a weak classifier to minimize the residual exponential loss, right? And it does so by creating this weighting scheme that turns out to be equivalent to the exponential loss of each training example, right? And then it trains a weak classifier on this training set to minimize this step of weighting. And in the homework, you will actually rigorously prove that this is what happens. So there's a few steps, and the homework walks you through all the steps, so you don't have to do everything in a structured way. Formally prove the exponential loss of profound 0-1 loss. This is for free. It's in the slides. Relate exponential loss to this to the normalization constant term. That's important in the proof. And then finally, this is probably the most free-form part of the homework assignment, is you have to figure out why this is the right step size. Right? If you're going to view this from the perspective of functional gradient set, minimizing the residual exponential loss, why is this the right step size? And it's just a little bit of calculus. No big deal. Any questions on that? Yes?
So this approach sounds very much like statistical mechanics and physics. And so I was wondering, is there a different name for this?
So can you tell me why it's similar to statistical mechanics?
Because of the z factor and the exponential distribution.
Oh.
Like it sounds very much like Boltzmann's factors.
Yeah, so yeah, we're minimizing, well, I mean, exponential loss, okay, I see what you're saying. First of all, we will be seeing things that have tighter connections to statistical mechanics later in the course,
okay,
where we can interpret what we're minimizing as some notion of beta-free energy. In this particular case, I think the connection is fairly superficial.
Okay.
We call the normalizing constant z because we borrow that notation from statistical mechanics, right? In more complicated settings, the partition function, just like in statistical mechanics. In this particular derivation, even though the notation is inspired by statistical mechanics, the actual derivation is quite different.
Okay.
But we will see later on in the course, particularly when we get to probabilistic models, that we borrow a lot of concepts from statistical mechanics.
Okay.
Yes?
At what point would a weak model become strong? And is there any harm in running a strong model through this?
If you have a strong model, it already has low bias. So doing this thing won't actually improve, like in one step, right? So if you have a strong model, so let's take a look at this formula, right? If as epsilon goes to 0, what happens here? You get log of 1 over 0. You get log of infinity, right? So you get infinity, right? So if you have a model that perfectly classifies the training set, that it gets all the steps. It gets all the weight in the ensemble, right? So because one of these guys gets an infinity, right? Or practically infinity. So this whole framework doesn't work. Like if you can just basically learn everything as well as possible in one step, then you can't actually do much on the residual. Yeah. Does that answer your question? Yeah. Yeah. Yes?
So when we were talking about the squared loss a few lectures ago, you said that it was very sensitive to outliers. Is this even more of a problem?
Yes. This actually, yes. If you look at this loss function, indeed, it is quite sensitive to outliers. And that is one of the limitations of AdaBoost. Yes. Yeah, it's very sensitive to outliers. Yeah, it's a limitation. But that's why you use low bias, low variance model classes. Yes.
To follow up on that question on the outliers, do you ever in practice remove outliers manually from a training set?
In practice? Yeah, sure. Yeah, people do that all the time.
Okay.
Yeah. I mean, the theoretical way that we think about machine learning, you know, obviously doesn't, if you just throw in outliers, you're changing the distribution, right?
Yeah.
So, you know, a lot of the, at least the simpler theory would just fall apart.
Yeah.
But in practice, of course, people do that, and when it's appropriate, yeah. And there are, you know, of course, more complex theoretical ways of thinking about outliers that can actually explicitly account for that. We're not going to talk about that in this class. Okay, so just to recap, AdaBoost, again, is gradient descent in some kind of function space, a space of weak classifiers. The final model is a linear combination of weak classifiers, i.e. a point in this function space, right? And it iteratively creates a new training set by reweighting the examples in the original training set, and this reweighting is derived by minimizing the residual exponential loss. So that's a summary of AdaBoost. Unless there are any questions, I can move on to the final part of the lecture on ensemble selection. Okay, ensemble selection. So, you know, we spent a lot of time the last two lectures talking about the bias variance decomposition, thinking about model classes with high bias and low variance, or vice versa, and like really like delving into the nuts and bolts of this decomposition in order to derive these meta-learning algorithms, these ensemble algorithms that can optimize this trade-off along in different ways, right? And so, you know, we talked about two ensemble methods in great detail, right? Bagging, which averages high variance, low bias models, which intuitively will reduce the variance, and indirectly deals with bias by using low bias base models, like really, really deep decision trees. Boosting carefully combines simple models, right? And so therefore it reduces the bias of the overall model, of the final model, and it indirectly deals with variance by only using low variance based models, right? Can we get the best of both worlds, right? And so here's an insight, right? Why don't we just, instead of trying to like carefully tease out the bias and the variance, you know, what we actually care about is minimizing test error, right? And the bias variance decomposition is just a way of sort of analyzing test error, or reasoning about test error. We also have another way of measuring test error, which is use a validation set, right? The validation set says, you know, it gives us a measure of the test error, and it's a proxy for test error, right? And so rather than even thinking about the bias variance trade-off, just say, let's just try to minimize error on the test, on the validation set. And so that's how ensemble selection works, right? So we have the original training set. We split the training set into the smaller training set and a validation set, right? We train a whole bunch of models, a wide range of models. Some of them high bias, low variance, some of them vice versa, whatever, on S prime, the partition that we're going to use for training. And then we're going to maintain an ensemble, right, as before, as some combination of the models we use that we train, right? And then we add the model from this space of models we train that maximizes performance on the validation set. We don't care if it's because it, you know, it reduces the bias or reduces the variance. It doesn't matter. Whatever minimizes error on the validation set. And we repeat. Right, so the models are trained on S prime. The ensemble is built using V prime. Right, so in some sense, we're going to reduce some combination of bias and variance, whatever combination makes the most sense in terms of minimizing error on the validation set, which is a proxy measure for the test error. Right, so bagging reduces variance of low bias models, boosting reduces bias of low variance models, ensemble selection, who cares, as long as we're doing well, right? We use validation error to approximate test error. We build the ensemble to directly minimize validation error. We don't worry about the bias variance decomposition, period. Any questions? Okay. Of course, there's a catch. It sounds too good to be true, and it is too good to be true at least 100% of the time, right? The catch is that this whole premise is based on having a validation set, right? And what that means is that you require the validation set to be sufficiently large to be useful, right? And in practice, it also means that you have your original training set, and then you have to partition it into your actual training set and this validation set to use for building your ensembles, which means that you have less data to train your base models on your training set, right? Because unlike bagging and boosting. And so because of that, the base models might have weaker performance than what you might otherwise get if you were using the entire training set. So this does come at a cost. So it's not always going to work better than bagging and boosting, but oftentimes it works very well in practice. So for example, here is one comprehensive, very, very comprehensive set of experiments where they are measuring performance over a whole range of data sets across a wide range of measurements, accuracy, mean square error, etc. And the ensemble selection, was the best performing model learning approach. There's bagging, there's boosting. And in fact, ensemble selection for a long time was basically used to win, almost every machine learning competition. Keep that in mind for the academic project. So it's a very powerful idea. Again, it doesn't not always guarantee to work because it does come at a cost of statistical inefficiency because you are partitioning your original training set into smaller and smaller sets. Any questions on that? Yes?
If you're using the validation set to pick which models you add to your ensemble model, do you run the risk of kind of like overfitting to the validation set?
You do. I mean, the hope is that that process of selecting models to add is a fairly light process. So you're not, but you do run the risk, yes. And the quote unquote correct thing to do is to do another shard to do early stopping, right? Right. You have your training set, your ensemble selection validation set, and your early stopping validation set, right? But that divides things even further, right? And so these are the types of trade-offs that we can start maybe potentially think about theoretically, although it's beyond the scope of this course. In practice, people just sort of understand that these are trade-offs they make, and then figure out through trial and error how to best optimize it. Any other questions? Okay, so there is a bunch of references on Ensemble Method. So this is the end of the Ensemble Methods part of the course. There's a bunch of really interesting papers that have been published over the last 10 to 15 years on Ensemble Methods. I think, at least in industry, right, these are still the predominant ways that people get the best possible performance. You just build ensembles of your base models. People even build ensembles of deep neural nets, which is a scary thing to think about. But this is definitely, if you go off into industry and get a job, and your boss tells you, I want you to get the best possible performance, right? Because every 0.1% is worth millions of dollars. This is what you do. Okay, so that's it. Next 2 lectures will be on deep learning. They'll be taught by my PhD student, Joe Marino. And there's a tutorial on Keras, which is a deep learning package you're using for your homeworks this Thursday. That's it.